Okay, well, welcome back. Over the next few weeks, we are going to begin to narrow our focus towards understanding how forests function, from the ecosystem scale down to the individual tree. But for this week, we will begin with an overview of how, as natural resource managers, we classify forest land based on climate and site variables. This is a very important step if our goal is to manage our forest resources utilizing ecosystem processes as a model. To start, this first image here is of the Cane River watershed, which is located on the north side of Mount Mitchell in Yancey County, a county in western North Carolina which borders Tennessee. If you look to the left of the image along the slopes and ridges in the foreground and beyond, the dark conical-shaped trees are mostly red spruce with a few scattered Fraser fir. Here in North Carolina, you only find those species at high elevations, generally above 5,000 feet or so, below which they're replaced by other species. At latitudes further north, take Maine for instance, spruce and fir are widespread and abundant at elevations much lower. So the idea here is to start thinking about some reasons why that may be the case. This is what you may find if you hike downslope to roughly 4,500 feet elevation within that same watershed above the Cane River. This is a really good example of what can be referred to as the northern hardwood forest natural community. That big 35-inch, 36-inch sugar maple in the center is over 125 years old or so, and it's surrounded by yellow birch and American beech of various ages. This particular natural community is unique to elevations ranging from 4,000 to 5,000 feet in the southern Appalachians, but it comprises the majority of the forest land throughout Vermont and much of New England. So again, why do you think that may be? Start thinking about how growing conditions change based on elevation and latitude. If you were to travel from the Cane River watershed to New England, keeping at that 4,500 foot elevation, here's what you would find. In New England, 4,000 feet elevation is roughly tree line, above which the local site conditions don't even allow trees to grow. In the southern Appalachians, trees grow all the way up to the top of Mount Mitchell, standing at about 6,680 feet or so, is the highest point in the country, east of the Mississippi. The environmental variables that result in such a change in growing conditions is what we're going to examine here as we begin to discuss the classification of forest land at various scales. The first concept regarding forest classification is that of the ecosystem. As communicated by McAvoy in our textbook, an ecosystem is defined by the interaction of living organisms and the environment that supports them. So based on that definition, ecosystems have an elastic spatial scale. They can be very big or very small. There is no set size. So the image on the right displays a lichen, which is a composite organism consisting of symbiotic fungi and algae. That can be considered an ecosystem. Some people have argued that the Earth can be classified as one large ecosystem, given the interdependent relationships among living organisms and the non-living portions of the environment, like water, soil minerals, and oxygen, that support the existence of the living organisms. What we are concerned with primarily in this course are forest ecosystems, where there are many biotic or living organisms that interact, the most obvious of which are trees. There are many ecological factors that dictate which trees will grow and where, and for that matter, whether trees will grow at all. There are trees here on the slide growing within Panthertown Valley because it is situated within what we consider to be the temperate forest biome, an area of the world where broad climatic patterns are conducive to tree growth. We will discuss the classification of biomes coming up next. The type of trees present, including the Table Mountain pine off to the left on the rock outcrop, the white pine growing in the valley below, and the mixture of oak and other hardwood species on the slope across the valley, are influenced by local growing conditions based on smaller scale site variation. We will discuss the nature of this variation and how we classify forest land at the local scale or the site scale later in the lecture. The biome is the broadest ecological classification that we will examine in this class, the distribution of which are determined by broad climatic patterns, temperature, and soil conditions. We will look at 3 forest-centered biomes here: the temperate forest biome, the boreal forest biome, and the tropical forest biome, though there are several other non-forest biomes like desert and aquatic-based biomes as well. We live in the temperate forest biome, where there are well-defined seasons, a moderate amount of precipitation evenly distributed throughout the year. This biome is present throughout much of the eastern U.S. as well as in parts of Northeast Asia and parts of Western and Central Europe. Because of our moderate temperatures and well-distributed precipitation, our soil is inherently fertile and productive. The term fertile implies that the soil is capable of providing soil nutrients and moisture sufficient to grow and sustain forest land. As a result of these conditions, our forests tend to have multiple layers of vegetation from the forest floor to the canopy, and they tend to support a relatively high variety of species as well. The growing conditions of the boreal forest, or taiga, to our north is very different. This biome is the world's largest terrestrial or land-based biome. It's found throughout Canada, Alaska, Siberia, and Scandinavia. As you may expect, cold temperatures are common in the boreal forest, particularly in the winter. Summers are abbreviated, but that is when the majority of the precipitation occurs. The soil is generally thin, nutrient-poor, and acidic, offering less of what trees need to grow. Because it's so cold, the decomposition rate of soil organic matter is really slow, and therefore it offers limited soil nutrients to support tree growth relative to the temperate forest. Also, the soil is seasonally frozen, offering less soil moisture required for tree growth as well. Conifer species, evergreen trees capable of tolerating such conditions like black spruce and jack pine and tamarack, often maintain dense foliage and permit little light into the understory and forest floor. Because of the conditions, there is less structural diversity in the boreal forest compared to the temperate forest, and definitely compared to the tropical forest, which we're going to examine next. Tropical forests are concentrated along the equator in areas like Brazil, Indonesia, and Peru for climatic reasons that we're going to examine in a moment. Here, temperatures vary very little, remaining warm throughout the year. In addition, precipitation exceeds 80 inches annually. The distribution of that precipitation throughout the year varies locally. Though counterintuitive, the soil of tropical forests is inherently less fertile than that of temperate forests for a couple of reasons. First, because of all the precipitation, soil nutrients are subject to leaching. The term nutrients refers to elements like nitrogen and phosphorus that exist in soil solution and are needed for tree growth. Over an extended period of time, those nutrients may be carried by precipitation down through the top layers of soil to where trees may no longer access them. Additionally, given the consistently warm temperatures within this biome, the decomposition rate of organic matter within the soil is really very rapid, and those recycled soil nutrients are used readily by the growing vegetation. So what you end up with is a forest far more structurally complex than those of the other biomes, with often 5 distinct layers of canopy vegetation, and also a forest in which there may be over 1,000 distinct tree species present. But the soil below the forest is less resilient to disturbance. If you can think of soil nutrients like currency or like money, the temperate forest is kind of like a person who chooses to store the majority of his or her money in the bank, in this case the soil, and only carry around a small percentage of it in his wallet, in this case the trees. In this analogy, a tropical forest would more closely resemble an individual who chooses to carry the majority of his money in his wallet, with very little left in the bank. If trees are cut to a significant extent in the temperate forest, or that gentleman's wallet is taken in a robbery, there's plenty of money in the bank to recover, or in this case nutrients in the soil to grow new trees. That's not true for the man who represents our tropical forest. If his wallet is taken, there is little money left in the bank to rebuild. The same is true for large-scale tree removal in a tropical setting. The majority of necessary nutrients often leave with the trees themselves. The global distribution of biomes is influenced greatly by climate. It's important to first recognize that climate and weather are fundamentally different. Weather fluctuates daily, while climate is sort of a prevailing condition determined by the amount of solar radiation an area receives, the type of precipitation patterns present, and the arrangement of land masses relative to large bodies of water. Weather is determined by the dynamics of air masses aloft, and weather changes frequently. We can separate the world into climate groups based on the air masses that are characteristic of each area. The climate conditions of any area of the world are driven by the relative influence of tropical and polar air masses. Here in the middle latitudes, where we have temperate forests, we are influenced by both, and as a result we have a highly variable weather season to season.